Master Math, find Mr. Wang. Hello everyone, I am that Mr. Wang. Today, let's explore together this challenging multiple choice question from the 2016 Haidian first year final exam. What makes this question difficult? The difficulty lies in the fact that it involves several parameters, and when these two general functions are combined, many students don't know how to judge the problem. It says that there exists a minimum value on the interval from 0 to positive infinity. Let's think about it. What does the extremum of a function depend on? It definitely depends on monotonicity. So next, we'll substitute options A, B, C, and D one by one to study the monotonicity of this function. All right, first, when A is less than 0, let's consider log base 2. It's an increasing function, right? If A is less than 0, then it becomes a decreasing function. And as for x squared on the interval from 0 to positive infinity, it's also increasing. You can compare it to an inverse proportional function, right? If b0 passing through the second and fourth quadrants, it's also increasing. Decreasing plus increasing is uncertain. Monotonicity is indeterminate. If 2b0, it's also decreasing. If b0, its opposite, also decreasing. So, decreasing plus decreasing, according to the monotonicity substitution principle, the whole thing is a decreasing function. Let's imagine a decreasing function on the interval from 0 to positive infinity. Where would it have a minimum value? It must be when x approaches positive infinity that it has this minimum value, which is negative infinity. We don't know that exact value, so B is wrong. Similarly, for C, when A is over 0, it increases. When B is under 0, it also increases. The sum is also increasing. An increasing function on 0 to infinity has a minimum at 0. But in our case, 0 is an open interval, so it can't actually take that value. So option C is also eliminated. Option D is similar. If A is positive, it increases. If B is positive, it decreases. Now we have options A and D. We know a minimum exists on 0 to infinity. By monotonicity, it must first decrease, then increase for a minimum to exist. At this point, we need to use what we learned in our advanced math class during the fall term, the wonderful use of graphs. We can use the graph of the function to determine the extremum. All right, first, let's draw option A. When A is less than 0, this log base 2 of x is flipped, so it becomes decreasing, like this. All right? Then when B is less than 0, it's increasing. Pay attention here, we can draw an analogy to the inverse proportional function. If you treat x squared as t, then it's b over t, which is increasing. So the graph looks like this. So when the two are combined, let's first look at it from the perspective of 0. On this side, it approaches positive infinity, and on the other side, negative infinity. When you add them together, it's indeterminate, because whichever changes faster will dominate. But we can look further ahead. You see, for the inverse proportional part, it approaches 0 from the positive side, so it can actually be ignored. Whether you add 0 or a negative number that's close to 0, it doesn't really matter. But for the logarithmic function here, it actually approaches negative infinity. So when this a times log base 2 of x gets close to negative infinity, that's infinitely small. How could there possibly be a minimum value when it's infinitely small? So there definitely isn't a minimum value. There's no minimum value at all, so we just pass on this case. So based on the process of elimination, we just choose 4D. All right, let's take a look. By thoroughly studying this problem, what have we learned? One thing is, when we talk about the existence of extreme values, what is it always related to in a function? It's related to monotonicity. Secondly, when determining monotonicity, especially when we look at the final exam questions from several main districts that have already been tested, most of the time you're not asked to use the definition method, like arbitrarily choosing x1 and x2 to judge. That's too cumbersome for multiple choice or fill-in-the-blank questions. So what can we use directly? Equivalent substitution, for example, increasing means increase, decreasing means decrease, and so on, using these kinds of methods to determine monotonicity. The last point is that when we use graphs to make judgments, some students might say that it's hard to visualize the sum or difference of two functions. But if you draw their graphs separately and study the so-called limiting cases, sometimes you can also figure out whether there is an extremum. All right, that's the explanation for this problem. I hope it can help everyone. Finally, as winter break is just around the corner, if any students want to use the break to get ahead, you can contact teacher Wang via private message. We will offer small group classes and one-on-one targeted tutoring. See you in the next class.